Hello, welcome to Chapter 2, Book Problems and Solutions. This lecture, this is number 3, is a lecture that contains all of the book problems and solutions. So make sure that you have your homework done before you look at this. And then if you have any question after you view this, please ask me in class the next day. What is the difference between force and net force on an object? Well, let's look at this before we look at the answer. A force is something that's applied to an object. A net force is two forces that combine their effect on an object. Or force is push or pull. Net force is the combination of all forces acting on it. What is the net force on a box that is being pulled to the right with a force of 40 newtons and pulled to the left with a force of 30 newtons? Well, it would be a difference of 40 and 30. You'd actually add them. However, you'd have to assign one of them positive and one of them negative, and then you combine them. And the answer would be 10 newtons, and it would be to the right. If you didn't combine them, you'd have to put your answer in terms of right or left. What is the net force on a box that is being pulled to the right with a force of 40 newtons and pulled to the left with a force of 30 newtons? Well, similar to the last problem, you'd have 40 to the right and 30 to the left. It would be 10 to the right would be the answer. Sounds awfully similar to the last one, but that might have been a mistake. Either way, the net force is 10 newtons to the right, and that may have been, but let's say it was 30 to the right and 40 to the left, then it would be 10 to the left. Either way, you're simply adding the two vectors and finding their sum, keeping track that they are indeed integers. What two quantities are necessary to determine a vector quantity? Well, a vector is something with magnitude and direction, where a scalar quantity is something with just magnitude. In chemistry, you learned mass, length, time. Those are all scalar quantities. So how does a vector quantity differ from a scalar quantity? Well, the vector quantity is only magnitude, and the vector quantity has both magnitude and direction. Again, scalar quantities such as mass, length, these are, there's no negative or there's no plus or minus length. Give an example of a vector quantity, give an example of a scalar quantity. A vector quantity would be any integer, force, velocity. Force is a vector quantity, time, area, and volume are scalar quantities. Again, you did all of those in chemistry, time, area, and volume. How much tension is in a rope that holds up a bag, that holds up a 20 Newton bag of apples at rest? Well, it would be 20 newtons. Remember, the tension is defined as the force within a cord. There's a cord, and then the force in the cord is actually called the tension of that. What does sigma F equals 0 mean? It means the sum of the forces equals 0. The sum of all forces equals 0. And in this case, That's going to be mechanical equilibrium. It means that the vector sum of all forces that act on an object in equilibrium equals 0. So that would be the definition of mechanical equilibrium, either static or dynamic. What is the net force on an object at rest? Well, you add up all the forces, and there's nothing, the object isn't being moved, so it would be at rest, so all the forces would be equal. The sum of all forces would be equal. For instance, sitting in a chair. You sit in a chair, the downward force equals the upward force. The downward force is your weight, the upward force is called the normal. No movement. When you do pull-ups and you hang at rest, how much of your weight is supported by each arm? Well, it would be half of your weight. As long as the arms are vertical, each arm would be half your weight. If they are horizontal, then the tension in each arm would be infinite. It would be utterly impossible to do that, despite what people may say to you, or what the Olympics may be. If you look at the Olympics carefully, it's not true. They're not completely horizontal. What is the angle between a support force and the surface on an object? Surface on object rests upon 90 degrees. Support force is perpendicular, normal, to the surface. It says, what two forces compress a spring inside a weighing scale when you weigh yourself? Well, it would be, what do you think? It would be definitely your weight. It would be the downward push due to gravity and the upward force of the floor. The upward force is called the normal. The downward force is called the weight, or the force due to that weight. What's next? When you are at rest and supported by a pair of weighing scales, how does the sum of the scale readings compare with your weight? The sum of the readings will equal your weight when you are at rest. The sum of the readings will equal your weight when you are at rest. 14, can an object be moving and still be in equilibrium? And the answer is absolutely. For instance, you're in outer space and you're moving. There's no force being applied to you. However, you're still moving. When you have no net force, you have constant velocity. When you have a net force, you have acceleration. So yes, if it moves at constant speed in a straight line, then the sum of the forces equals 0. So if you have a net force, you would have acceleration. If the net forces are 0, then you have constant velocity. Okay, if you push a crate across a factory floor at constant speed and constant direction, what is the magnitude of the force of friction on the crate compared with your push? Well, it would be the same, because you're going at a constant velocity. If you think about it, the only force you're applying is to keep it constant, and what would stop it ultimately would be the friction. Distinguish between static equilibrium and dynamic equilibrium. Static equilibrium is when the forces are 0 at rest, and dynamic equilibrium is when something is at a constant speed, as is the answer here. Objects are at rest, static equilibrium, they're moving at constant speed, that's dynamic equilibrium. According to the parallelogram rule for two vectors, what does the diagonal of the constructed parallelogram represent? Well, it represents the resultant. The diagonal is the resultant, or the sum of the two vectors, using the component method. I could use the component method to do it, or simply state that graphically. Consider the suspension of Nellie in figure 211. Name the three forces that act on her. What is your evidence that they cancel to zero? All right, this is Nellie. This is 211. Nellie's weight is shown by the downward vertical vector. An equal and opposite vector is needed for the equilibrium shown by the dashed vector. B, this dashed vector is the diagonal of the parallelogram defined by the dotted line. C, both rope tensions are shown by the constructed vector. Now, as you know, each cord, each support string is going to have its own tension, and the tensions will be the same. If they're the same length, they're going to be the same tension, and the angle that's created between the vertical and the cord or the hypotenuse, if I know that angle or I can measure that angle, then I can determine the tension in the wire, because I know that the vertical vector is half the load. So if I have the angle and I know half the load, I can determine the vector. So I can do this quite easily in terms of trigonometry, as we've seen before. So let's see what the book says relative to the original question, and we'll see how well we did. Just remember, you're going to have to do this quiz on Tuesday after the test, so make sure that you know how to do this perfectly well. Okay, downward force is weight. Two upward forces are tensions in ropes. Being at rest in equilibrium is evidence that the sum of the forces equals zero. Okay, consider Nellie in figure 212. What changes in rope tension occur when the ropes make a greater angle with the verticals? And so what are we going to say? We're going to say that, well, the tensions are going to increase rapidly. You know, the larger that angle is between the tension and the vertical. Okay, we see that the rope tensions increase, and the tension will become, as I said, infinite as that rope, as that angle approaches 90 degrees. All right, next. When Nellie hangs from ropes at different angles, as shown in figure 2.13, how does the vector resultant of the two rope tensions compare with her weight? Compare with her weight. Here the rope supports Nellie have different angles. Note that the tension is unequal in the two ropes. That's true, but that's really not what we're asking. We're asking, how does the vector resultant of the two ropes compare? Well, the resultant of both rope tensions is equal in magnitude and opposite in direction to the vector representing her weight. Even though each rope has a different value, the sum, the results of both are going to be equal in magnitude and opposite in direction. Rank each of the following sets of scenarios in order of the quantity or property involved. List them from left to right. If scenarios have equal rankings, then separate them with an equal sign. That is, or example is A equals B. All right, 21. Blocks A and B are supported by the table. Block C is partly supported by the table and partly by the rope. Rank the support forces provided by the table from greatest to least. All right, now, so we want to rank blocks A and B from greatest to least. Well, what do you think? A and B seem to be equal. You have the right side is going to be 10 newtons, so the left side should be 10 newtons. What do you think? So, A, B, and C looks like they might be, and they are, all equal. All equal. Block C is partly, it says blocks A and B are supported by the table. Rank the support forces provided by the table from greatest to least. So you can see that they're all the same, all exactly the same. So not too bad. Okay, next. In the diagram below, or the next page, identical blocks are suspended by ropes, each rope having a scale to measure the tension or the stretching force in the rope. Rank the scale readings from greatest to least. Rank the scale readings from greatest to least. Okay, here we go. Let's see. A is going to be supported by 3. Okay, so they're all going to be equal. B is going to be one thing, they're all right, they're all equal, I guess. So D, the scale reading should be the same for both. So let's see, A is divided into 3s, B and D are the same, and C is divided into 2. So yeah, B and D are equal, and then it would be C and then A. That makes perfect sense. Okay, look that one over. That's a little bit confusing, but you should be able to do that. Burl and Paul stand on their sign painting scaffolds. Tension in the left rope is measured by a scale. Rank the tensions in that rope from greatest to least. The greatest tension to the least tension on the scaffold. Okay, let's see what it says. Right. Burl and Paul. Okay, so looks like it's going to be A is going to be the blue guy, whatever the blue guy is, blue and green guy. And then looks like A and C should be the same. A and B should be the same. C looks like it's going to be blue and green guy almost together, so that'll be larger. And then D would be a little bit less, and that's right. C, D, and then A and B are equal. So C would be greatest, D would be next, because he's running away from the other guy, and then A equals B. So that makes absolute perfect sense. Absolute perfect sense. So, a very important problem relative to mechanical equilibrium and the distribution of forces. Percy does gymnastics suspended by one rope in A and by 2 ropes in B, C, and D. Rank the tensions in the ropes from greatest to least. Percy the gymnast. Okay. A would be probably the greatest. No, D would be the greatest because of the angles. C would be, A would be next, then C, and then B would be the least because it's half his weight in each. So it would be D, A, C, B. D, A, C, B is correct. What do you think? Did you get that one correct? Okay, the cat lies on the floor. Can you say that no force acts on the cat, or is it correct to say that no net force acts on the cat? Well, of course forces act on the cat. You have the cat's weight, which is the downward force, and the cat's supporting force, which is the normal force. So yeah, they're going to be no net force, but there's certainly going to be forces acting on the cat. Consider 2 forces, one having a magnitude of 20 newtons, the other having a magnitude of 12 newtons. What is the maximum net force possible for these 2 vectors? What is the minimum? Well, the maximum would be 32, and the minimum would be 8, because you add them, you get 32, you subtract them, you get 8. So that's very, 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 very straightforward. Actually, does that make sense? If you put them opposing, maybe at an angle, but as it's written, that's certainly reasonable to assume that that's correct. Number 27, when a box of chocolate bars is in mechanical equilibrium, what can be correctly said about all the forces that act on it? Must the net force necessarily be 0? Well, if it's in mechanical equilibrium, the net forces have to be 0. That's the first thing. So when a box of chocolate bars is in mechanical equilibrium, what can be said correctly about the forces acting on it? Well, the sum of all forces, i.e. the net forces, must be equal 0. Yes, it's in mechanical equilibrium. If it's moving at a constant speed, it would be in dynamic mechanical equilibrium, and if it was at rest, it would be static equilibrium. But either way, no matter how you slice and dice it, it would be in mechanical equilibrium. So yes, and in mechanical equilibrium. Faina says that an object cannot be in mechanical equilibrium when only a single force acts on it. Do you agree or disagree? I agree. If only a single non-zero force acts on an object, it will be in mechanical equilibrium. There must be one or more additional force to produce a 0 net force for equilibrium. So I would absolutely agree. You need more than one force, otherwise no dice. Okay, Phyllis Physics hangs at rest from the ends of a rope, as shown at right. How does the reading on the scale compare to her weight? Okay, let's look at Phyllis Physics. And let's see, what's the question? How does the reading on the scale compare to her weight? Well, how many strings are supporting her? Well, there's 2 strings. The fact that she's on a little bit of a swivel thing means nothing. It should be half, right? So it reads half her weight. So the upward pull of the left rope plus the upward pull of the right rope minus her weight will equal 0. And we will learn how to do a free body diagram when we start to do this. It's going to become very important. A free body diagram. Okay, this one's a little long, so let's take this slowly. Harry the painter swings year after year from his bosun's chair. What is a bosun's chair? You should look that up. Bosun's chair. His weight is 500 newtons, and the rope, unknown to him, has a breaking point of 300 newtons. Well, isn't that reassuring? Why doesn't the rope break when he is supported as shown at the left? Well, we're going to have to look at that figure in a moment. One day, Harry is painting near a flagpole, and for a change, he ties the free end of the rope to the flagpole instead of to his chair as shown at the right. Why did Harry end up taking an early vacation? Let's read that problem again. Harry the painter swings year after year from his bosun's chair. His weight is 500 newtons, and the chair, unknown to him, has a breaking, and the rope, unknown to him, has a breaking point of 300 newtons. Why doesn't the rope break when he is supported as shown at the left? One day, Harry is painting near a flagpole, and for a change, he ties the free end of the rope to the flagpole instead of to his chair, as shown at the right. Why did Harry end up taking an early vacation? As they say, when the plot thickens, the plot thickens. Harry's bosun chair. So what I'll do is, after this slide, is finished, I will look up bosun's chair and tell you what a bosun's chair sounds like. Very nautical, doesn't it? A bosun's mate. What is a bosun's chair? Okay, so Harry and the bosun chair. Be right back. It is obvious here that each string on the left carries half his weight, and the string on the left, the one that's directly attached to his chair, is carrying his entire weight. So at left, Harry is supported by two strands of rope that share his weight, like Phyllis in question 29. So each strand supports 250 newtons below the breaking point. At right, Harry is supported by just one strand, which requires a tension of 500 newtons. This is above the breaking point of the rope, which breaks and changes his vacation plans. Vacation plans. Okay, how many significant forces act on your physics book when it is at rest on a table? Identify the forces. Two forces, weight and the supportive force. Weight and the normal force, to be exact. Why doesn't the support force that acts on the book resting on the table cause the book to rise from the table? Because it's counterbalanced by the weight. The weight equals the normal force. The book doesn't rise because the net force on it is zero. Weight minus support force, or normal force, equals zero. Nicole stands on the bathroom scale and reads her weight. Does the reading change if she stands on 1 foot instead of both feet? No, the leg will, no, the reading is the same. Pressure against the scale is less on 1 foot, but not the weight. Justin sets a hockey puck sliding across the ice at a constant speed. Is the puck in equilibrium? Why or why not? Yeah, it's constant speed, so it's at dynamic equilibrium, mechanical equilibrium. Yes, it is a dynamic equilibrium. It is not undergoing a change in its motion. Constant speed, that's the key. Alyssa pulls horizontally on a crate with a force of 200 newtons and it slides across the floor at a constant speed in a straight line. How much friction is acting on the crate? 200 newtons. Constant speed in a straight line. So the sum of the force equals zero. Force of pulling is friction. Consider a heavy refrigerator at rest on a kitchen floor. When Anthony and Daniel start to lift it, does the support force on the refrigerator provided by the floor increase, decrease, or remain unchanged? What happens to the support force on Anthony's and Daniel's feet? What happens to the support force on Anthony's and Daniel's feet? Support force on the refrigerator decreases as it's lifted. When entirely lifted from the floor, the support force provided by the floor is zero, and the support force on the men's feet increases as the load transfers from the floor to them. We'll explain that a little bit further when we do Newton's laws of motion. Sneezlee is supported by two thin wires. Is the tension in each wire less than, equal to, or more than half his weight? Use the parallelogram rule to defend your answer. Well, before the next slide, if it were vertical, it would be, each wire would be equal to half his weight. But as you know, if it were perfectly vertical, then the tension of each wire would be half of Sneezlee's weight. But the wires are only nearly vertical, so tension in each wire is greater than half the weight. That's all you can really say. We know that it's more than half the weight, each wire. And the greater that angle between the wire and the vertical, the greater the tension in each cord. Sneezlee's wire supports are repositioned as shown. How does the tension in each wire compare with the tension of the previous question? Well, I don't have the picture there, but the wires are at even a greater angle. The angle between the vertical and the wire is greater. than the last picture. So the greater the tension, as the parallelogram would show, interestingly, a 60-degree angle results in the tension equal to the weight. If angle exceeds 60 degrees, tension in the wire exceeds the weight. So just remember, the greater that angle between the vertical and the cord, the greater the tension in the leg, in the cord. If a picture frame were supported by a pair of vertical wires, tension in each wire would be half the weight of the frame. When the frame is supported by wires at an angle, as shown below, how does the tension in each wire compare with that of the vertical wires? Well, again, as that angle between the vertical and the cord increases, so does the tension. Tension in each wire is greater than half the weight of the picture. The next one is going to have only one cord. So if that one cord were vertical, it would be equal to the monkey's weight. A monkey hangs by a strand of rope and holds onto the zoo cage as shown. Since her arm holding the cage is horizontal, only the rope supports her weight. How does the tension in the rope compare with her weight? Well, it's going to be at an angle. If it were perfectly vertical, then it would be equal to the weight. So the tension in the rope is greater than her weight. Now, as that angle between the cord and the vertical approaches 90 degrees, then the tension in the cord approaches infinity. So chain tensions on both sides of the book must form a parallelogram with a resultant that equals the weight of the book. This can only occur if each side of the chain makes an angle to the horizontal. It's not well explained. We know from trigonometry that the angle between the chain and the vertical will approach 90, therefore it will approach infinity. That's a better answer to that. Two vertical chains are used to hold up a 1,000 Newton log. One chain has a tension of 400 newtons. Find the tension in the other chain. From sum of the forces equals 0, total upward tension weight of log 400 newtons plus tension in the other chain equals 1,000 newtons. Tension in other chain equals 1,000 newtons minus 400 newtons, which equals 600 newtons. Lucy Lightweight stands on one foot on the bathroom scale and her other foot on the second bathroom scale. Each scale reads 300 newtons. What is Lucy's weight? Well, it would be 300 in each leg. It would, for a total of 600 newtons. Total of 600 newtons. Okay. Again, symmetry is understood there. Harry Heavyweight, who weighs 1,200 newtons, stands on a pair of bathroom scales so that one scale reads twice as much as the other. What are the scale readings? You could set up an algebraic equation, but it's clear here that one's going to be 400, the other one's going to be 800, and that will equal 1,200 newtons. But you could, again, set up an algebraic equation, solve for one of the variables, and then plug back into the equation. The sketch shows a painter staging in mechanical equilibrium. The person in the middle weighs 250 newtons, and the tensions in both ropes are 200 newtons. What is the weight of the staging? Using simple analysis here, we see that the staging weighs 150 newtons. Remember, the upward, which is 400, must equal the downward 400. Opposite and equal, equal and opposite. So 400 minus 250 is 150. Very straightforward. Just remember the summative equation at the bottom in orange. A staging that weighs 300 newtons supports two painters, one 250 newtons and the other 300 newtons. The tension in the left rope is 400 newtons. What is the tension in the right rope? Again, the downward and the upward must equal. So what do you think? What is the total upward? The total downward is obviously 850. So 400, so 850 minus 400 would be what? 850 minus 400 would be 450 newtons, and that is indeed the answer. Remember, 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 especially when we talk about the monkey problem. Remind me to talk about the monkey problem. The upward force total must equal the downward force total. When we talk about torques, we talk about the same thing. The upward sum of the upward vectors has to equal the sum of the downward vectors. The sum of the upward vectors must equal the sum of the downward vectors. Very, very basic. One of the most important elements in all of physics. Two children push on a heavy crate that rests on a basement floor. One pushes horizontally with a force of 150 newtons, and the other pushes in the same direction with a force of 180 newtons. The crate remains stationary. Show that the force of friction between the crate and the floor is 330. I'm not sure I read that correctly. One pushes horizontally with a force of 150 newtons. The other one pushes the same direction with 180 newtons. And show that the force of friction between the crate and floor is 330 newtons. Okay. Well, if you push on a wall with, say, 500 newtons, the wall's going to push back with the same amount, 500 newtons. Why? Because the wall's not moving. You're not moving, the wall's not moving. So the wall has to be pushing back equal to what you're pushing. So if the children push at a total of 330 newtons, then the floor must be pushing back at 330 newtons. What aspect of the floor is actually pushing back? And by inspection, you should be able to detail that indeed it would be caused by the friction. So it's the friction that's 330 newtons. Two children push a crate. They find that when they push together horizontally with the force of 155 newtons and 187 newtons respectively, the crate slides across the floor at a constant speed. Show that the force of friction between the crate and the floor is 342 newtons. 342 newtons. Well, the key here is that the crate moves at a constant speed in a straight line. So sigma f equals 0, sigma f's down or in one direction equals sigma f's in the other direction, so that 150 newtons plus 187 newtons in one direction will equal the force of friction, which is 342 in the other direction, in opposite directions to the children pushes. Okay, so the idea is that if the children are pushing, it's going at a constant speed, they're just pushing just enough for the crate to be moving at a constant speed, or just enough to overcome the friction.